I'm exploring the fascinating world of plants, from the most bizarre to the most beautiful. I will be using today's latest technology to reveal a whole new dimension in the lives of plants. I'll trace them from their beginnings on land to their vital place in nature today. And discover a hidden world that only too often we overlook. We will move from our timescale to theirs. Explore the extraordinary ways by which some plants survive in the harshest conditions. And we will do all this in one unique place, a microcosm of the whole plant world. The Royal Botanic Gardens at Kew. I've seen plants growing in their natural habitats all over the world, but here in Kew it's possible to examine them in a way that is impossible in the wild. Here some 90% of all known plant species are represented in one form or another. So in this one place you can survey the entire plant kingdom, and what is more, using 3D cameras, reveal some of its most intimate secrets. Plants flourish most dramatically in places where there is a lot of warmth and a lot of water, the wet zone. So here we can discover how plants first established themselves on land to become the very foundation of all terrestrial life. Rainforests occupy only about 2% of the world's land surface, but they contain over 50% of the world's species. And many of these wet zone plants have extraordinary survival strategies, and to study them, Kew has built a rainforest here on the banks of the Thames. This is a rainforest like no other. The palm house was constructed in 1844 from over 200 tons of iron and 16,000 panes of glass. No one had ever built a glass house on this scale before, and to do so the architects borrowed techniques from the shipbuilding industry, which may explain why the palm house looks like the upturned hull of a ship. Its purpose was to provide a home for the tropical plants that Victorian explorers brought back from their adventures in the tropics. It was an engineering wonder of the age. And it is still a botanical wonder. Most of the plants at this end of the house are kept in pots, as they would have been in Victorian times. And this is almost certainly the oldest pot plant in the world. This is Encephalatos altensteinii, and it came here in 1775. Altensteinii has since been joined by a multitude of other wet zone plants. Together, they constitute a unique global rainforest, a living laboratory where we can watch and observe the fascinating ways in which rainforest plants interact and behave. Conditions in this glasshouse are near perfect for wet zone plants. It's warm, it's humid, there's plenty of light, and as a consequence, plants grow very rapidly and all through the year. If you speed up time, plants begin to reveal their true nature. They're not passive organisms, as you might think, but competitive creatures, every bit as aggressive as animals. They're locked in a desperate battle for light and space. They stretch and pulse as they strive to barge their way into pole position. Creepers and vines reach around for the branch or stem of another plant on which to hitch a ride. Bamboos, a family of giant grasses, are capable of extraordinary speeds as they race towards the brightest light at the top of the canopy. They're the fastest growing of all plants. Some species can grow a whole meter in a single day. And at 30 meters tall, as high as a 9-story office block, they can compete with the tallest rainforest trees. The one resource wet zone plants don't need to fight for is water. In fact, there can be so much rain in the rainforest that some species have to have special ways of getting rid of it. This is the taro plant, and it has the most extraordinary leaves. Watch what happens when I pour water on them. The water rolls, leaving the leaf behind almost dry. And that's because the leaf is covered with very, very tiny microscopic structures which hold aloft the droplets of water. And as a consequence, only about 2% of water touches the actual leaf surface itself. And as the droplets roll away, they carry with them the dirt and bacteria. So in effect, these leaves are self-cleaning. But there are some plants that use water in a different way, and they live high up in the canopy. A tank bromeliad, a plant that is dispensed with the need of growing in the soil on the ground and instead attaches itself to branches up here in the canopy where there's plenty of light. And since it's so far from the ground, it has had to develop a technique of collecting its nutriment in a quite different way. They collect some of the rain that every day drenches the South American rainforest where they live. Their leaves, which are very broad, channel the rainwater into a central reservoir. At their base, the leaves are so tightly pressed together that the tank they create is watertight. Some species can hold up to 50 litres of liquid. The water not only hydrates the plant, but it also provides a home for a lot of creatures that wouldn't otherwise be able to live up here. These little wrigglers are the larvae of mosquitoes. In the wild, there are lots of different creatures that can be found in these little pools. This is Ranitomia imitator, a poison dark frog from Peru. It's the size of a thumbnail, and the only monogamous amphibian in the world. Some individuals spend their whole lives, from tadpole to adult, in and around bromeliad pools. And high in the canopy, such a pool provides an excellent home. It's relatively safe, and there's a ready supply of food. The plant benefits from the arrangement because the droppings produced by its lodger are a nutritious fertilizer. Bromeliads and the frogs that live in them are only one example of the complex relationships that abound in the rainforests. In tropical forests, the lives of every living thing, both animal and plant, are intimately entwined. It's a tangled web that has evolved over many millions of years. Throughout their history, rainforests have provided plants with a refuge against harsher conditions elsewhere in the planet. So in rainforests, you find some very ancient plant families. This cycad, for example, belongs to a family that certainly provided food for the dinosaurs. But the rainforest is such a rich environment that plants from all stages in their history can still be found here. The first were slimy, thread-like algae that emerged from rivers and swamps to grow on the wet, muddy margins. "40 million years or so later, some developed watertight coverings that enabled them to move onto drier, though still moist, land. They were the liverworts and the mosses. Later still, some of the descendants of those plants stiffened their stems so that they were able to stand upright as they reached up towards the light. They were the ferns and horsetails. This greening of the earth changed the course of life, allowing animals to follow plants out of permanent water. As they spread across the land, the plants pumped out oxygen from their leaves. So from the very beginning, land animals were dependent upon plants, not only for food, but for the very air they breathe. A major difficulty for plants in their new environment was reproduction. If they were to produce fertile seeds, pollen from one had to reach and fertilize the ova, the eggs of another. Conifers, pines, yews and firs then, as now, used wind. They produced vast numbers of pollen grains, scarcely bigger than particles of dust, which the wind could carry for hundreds of miles. The technique was successful, but very wasteful. Immense quantities of pollen grains had to be produced if just one was to reach its target. But then, about 140 million years ago, some developed a much more efficient way of doing that. With flowers. How this happened was, for a long time, a total mystery to scientists, including one of the greatest. Charles Darwin was baffled by what he called an abominable mystery. The fact that halfway through the age of the dinosaurs, flowering plants suddenly produced a vast number of species, and within a very short period of time. That contradicted one of the characteristics of evolution as Darwin saw it, that it was a slow and gradual process. How could that have happened? From the moment Darwin posed the question, scientists have been striving for an answer. Recent fossil discoveries and modern DNA analysis of species present and past have transformed our understanding of this fascinating period. Using that information, scientists with work pioneered here in Kew have been able to construct the ancestral tree of the whole of plant life. It begins with algae, the simplest of the plants, which are followed by the mosses. The thickness of the rising branches indicates the relative number of species in each individual group. For the first half of the plant's evolutionary history, all the branches of plant life flourished roughly equally. But then, 140 million years ago, there was an explosive radiation of species, Darwin's mystery. These were the angiosperms, flowering plants. Their evolution was more gradual than Darwin had thought, but there is no question that the angiosperms quickly became the dominant group. They diversified into a huge range of species, which have occupied almost every known habitat on Earth. But what happened to stimulate this dramatic radiation? There was a happy coincidence of two events. The first was a doubling in the genetic material of plants, allowing them to evolve more quickly when their environment changed. The second was one such change, the development of a unique relationship between plants and animals. The effect of this coincidence can be seen in one of the very first flowering plants to evolve. This is the water lily house, the hottest and most humid environment in Kew. It was built in 1852 to accommodate the latest botanical discovery, the giant Amazon water lily. Now it's February and the pond is almost bare, but in a few weeks exotic water lilies of all kinds will be sprouting. The ancestors of today's water lilies, as we know from their fossils, were among the first plants to produce flowers. Bright petals, modified leaves, were an advertisement to flying insects. They signalled the presence of highly nutritious pollen. The shape of the flower worked like a primitive trap, forcing the insects to stumble about and bump into the plant's reproductive structures. In doing so, the insects transferred onto the water lily pollen which they had accidentally collected on earlier visits to other flowers. So now plants could trick insects into transporting their pollen directly from one plant to another with a door-to-door service. The flower of the giant Amazon water lily can close totally, holding the insects captive for several hours, thus making absolutely sure that pollination occurs. Many different species of plant followed suit, each evolving its own particular flowers to attract its insect messengers. Competition for their services drove the plants to diversify. Insects favoured petals that were brighter, scent that was more perfumed, and flowers that had the sweetest nectar. The appearance of such temptations had a huge effect on the insects. They too began to diversify. A multitude of forms could better harness the potential of the numerous species of flower. Insects with large eyes could spot the flowers. Powerful wings could carry them between plants. And complex mouthparts could delve into the deepest nectary. So plants and insects evolved together, driving their mutual diversity. Rainforests are the culmination of this process, containing a greater variety of species than any other habitat. And here you can see that some plants didn't restrict themselves to insects. This, for example, is known as the jade vine. But why is it this extraordinarily mesmerizing blue-green color? Well, we know that it's fertilized by bats. That's why the flowers hang out in the open so the bats can get at them quite easily. And so maybe this color stands out particularly boldly as far as bats are concerned in the moonlight. When the bat arrives, it sticks its head into the flower to get at the honey, and as it does So, and presses there, out from this hook come the stamens and dab pollen on its back. So when the bat goes away, it takes the pollen to another flower. Each and every species of flowering plant has its own unique evolutionary story that's closely coupled with the animals that pollinate it. But one family of flowering plant has developed this relationship in more complex ways than any other, and in doing so has become the most numerous and diverse on the planet. There are an estimated 25,000 species of orchid. This family had a particular fascination for Charles Darwin, as he reveals in one of his letters that's kept here at Kew. He says, "I have been extremely much interested with Catasetum, that's an orchid, and indeed with many exotic orchids. Orchids have interested me as much as almost anything in my life." Charles Darwin. One species of these amazing plants can be found growing outside in the grounds of Kew. Orchids are extraordinary plants from many points of view, but one of them is that the lower lip of the flower is controlled by a special set of genes. So that means that it can evolve and change its shape and colour while the rest of its petals remain the same. The lower lip of this little orchid has evolved to look, roughly, like a bee. And people used to think that was a kind of warning, to warn cows not to eat it, on the grounds that they wouldn't want to get stung on the tongue. But now we know that's not the case. This is a mimic of a female bee that's attracting a male to mate it, and when the male mates, it will pollinate the flower. How do we know that's true? Because this little flower produces the scent which is exactly the same as that of a female bee trying to attract a mate. The unique genetic makeup of orchids has allowed them to evolve an almost unbelievable degree of complexity. And they produce their greatest variety and complexity in the wet zone. At Kew, they're cultivated inside the Princess of Wales Conservatory. In this section, conditions are perfect for them. Each orchid species has its own characteristic form and colour. They represent the pinnacle of evolutionary cooperation between animals and plants. In their most extreme form, the relationship for the plant is an exclusive one. Only one species of insect will have the right equipment to claim the plant's nectar. This relationship between a particular kind of insect and a particular kind of plant produces some extraordinary results. This, for example, is Darwin's favourite orchid, Catasetum. Unusually for orchids, some plants are male and others are female. This is a male. It produces a kind of scent that attracts just one species of small, glossy, beautifully coloured bee. The bee lands on the lip of the orchid and thrusts its head into the orchid's flower itself. And that touches a trigger and sticks onto the bee's back this extraordinary thing, which is in fact a bundle of pollen grains called pollinia. This has a little cap on it, which after a minute or so falls off and reveals there that little horseshoe-shaped bundle of pollen grains. High-speed cameras can show us the trigger mechanism. The pollinia accelerates with great force and so ensures that it sticks firmly onto the insect's back. The bee, no doubt somewhat dazed, flies away and maybe thinks it's not going to do that again, but is nonetheless attracted to another rather different-looking flower, which is the female, but which produces just that sort of scent. And it sticks its head into the female flower, and this little bundle of pollen, like a key, fits into a little aperture like a lock, and it pulls off the pollen and leaves on the bee's back a little bundle. And lo and behold, pollination has been achieved. It's hard to imagine how evolution produced such a complex pollination mechanism. But there is one orchid whose life story is even more astonishing. Many flowers produce a sweet nectar to entice insects and other animals to come and pollinate them. But this orchid from Madagascar, the comet orchid, carries its nectar at the end of extremely long spurs from the back of its flower. What on earth could have a tongue long enough to reach down those huge long spurs? Charles Darwin, who studied the fertilization of orchids, decided it could only be a moth, but nobody had ever seen it, until some years after his death he was proved right. This is Xanthopan morgani predictor, Morgan's predicted sphinx moth. With special night vision cameras, we can show why such an immensely long tongue is needed. It's 1/3 of a metre long. Exactly the same length as the spur beneath the flower. The relationship between orchids and their insect pollinators is certainly very intimate, but the connection between these passion flowers and butterflies is even more complex. This is Passiflora, the passion vine. Like orchids, its brightly coloured displays attract pollinators. One of them is a heliconid butterfly. But this relationship between an insect and a plant is no straightforward trade-off. Passion vine and butterfly have been engaged in an ongoing game of one-upmanship for many millions of years. The butterfly doesn't just want nectar. It also wants a place to lay its eggs. A place where its caterpillars will have something good to eat immediately nearby. Passion flower leaves. And its young have huge appetites. But some passion vines have fought back. They have evolved a way to protect themselves. Poison in their leaves. But sometimes even this is no defense. Some caterpillars not only tolerate the leaves' toxins, but store them in their flesh. And now those toxins serve as a defense against the caterpillar's predators. And the story doesn't even end here. The passion vine has evolved a second line of defense. This one has leaves that give the impression of being a swarm of butterflies. By mimicking the real ones, it may be suggesting that there is no perching room for others. And in the detail of their leaves, you can see something even more surprising. This kind of passion flower has a special way of dissuading female butterflies from laying eggs on its leaves. It imitates eggs with these little yellow spots, so that female butterflies will think that these leaves are already taken, as you might say. And this different species of passion flower does the same thing, but imitates eggs in a different way, with tiny little growths at the base of the leaf. The passion flower's tactics illustrate some of the complex ways by which plants dissuade animals from eating them. But some wet zone species have turned the tables. This bud will soon become a leaf. It's no ordinary leaf. It has a special, altogether more sinister purpose. This is Nepenthes, the pitcher plant. It grows in nutrient-poor soils, so has to find nitrogen and minerals in another way. The leaf, just like a flower, attracts insects with a reward. The pitcher is coloured and scented to appeal to flies looking for a meal of rotting flesh. The visitors are rewarded with a greasy substance on the underside of the pitcher's lid. But the plant wants something in return. Not pollen, but a meal. The lip of the pitcher is covered in tiny, slippery ridges. Wax lubricates the surface further. It's extremely difficult to hold on, even for a fly. Once inside, there's no escape. The leaf holds a pool of digestive liquid. This contains microscopic elastic filaments which give it the properties of quicksand. The more the insect struggles, the deeper it sinks. Enzymes begin to dissolve the victim's body while it's still alive. Some pitchers aren't content with just insects. This one eats mice. The mice come along, perhaps attracted by the sweet nectar on the lip. They fall in, they can't get a purchase to get out, they drown, and eventually the enzymes in the pitcher's fluid dissolves the body so that eventually there's nothing left but a bit of fur and bones. This pitcher is called Nepenthes lowii. It lives on the forested slopes of Borneo's mountains. And it's perhaps the most extraordinary pitcher of them all. The evidence is that it too attracts small mammals. It secretes a sort of nectar from the underside of the lid there. And that attracts little tree shrews. This engaging little animal is Tupaia montana, the mountain tree shrew. It feeds on fruit and any insects it can find. It also visits pitcher plants. Until recently, what happens next was a mystery. This footage seems to show that the animal has found a way of evading the slippery death trap. What is more, it's feeding on the underside of the pitcher's lid. This pitcher doesn't get its nutriment from the bodies of dead animals. It's got another way of sustaining itself. The tree shrews come to lick it, and when they do, their rear end is directly over the pitcher so that their droppings fall into it. And it's that that provides this plant with its nourishment. It's even been suggested that nectar contains a laxative to persuade the tree shrew to do just that. The stability of the rainforest environment over time has allowed the co-evolution of animals and plants to develop to an unrivaled degree of complexity. But with complexity comes fragility. Each and every species has its own place in the complex working of the rainforest. In recent years, Kew's unique position as a living laboratory of the wet zone has become more important than ever. These days, Kew's role extends far beyond these 300 acres. And here people are working to rescue extremely rare plants from total extinction. The danger of losing a single species is taken very seriously indeed. Here in the water lily room, experts face a desperate scramble to save one species from oblivion. Nestling amongst the giant water lily pads is the tiny Nymphea thermarum, the Rwandan water lily, the smallest and rarest water lily in the world. Extinct in the wild, these precious few individuals are some of the last remaining specimens. These photographs show its only known native habitat as it was over 20 years ago, a hot spring in Rwanda. It was destroyed just recently when locals redirected its waters to supply a laundry. A single specimen was brought back to Europe, but the species remained on the brink. Its seeds would germinate, but the seedlings always died. Then some seeds were given to this man at Kew, Carlos Magdalena. Known in Spain as the plant messiah, Carlos is famous for his great skill in rescuing endangered species. But even Carlos nearly met his match with this tiny plant.
I tested many different seedlings. Nothing seemed to work.
Well, that meant that the species was about to disappear forever.
Exactly, and that was very worrying for me. So I started becoming a little bit obsessed with it. Yes, I mean, it's just a bit distressing, isn't it? To know that something that you can do or not make a difference to a species.
Carlos didn't give up. He had one more unlikely idea. He tried growing the water lily out of water.
If you think about it, growing a water lily out of the water is something as crazy as trying to grow a cacti floating in a pond. So it was the last unlikely thing that logically you will do. And then that is the result.
Carlos's inspired idea was to make use of this plant's strange ecological quirk. Nearly all other water lilies only grow in deep water, but the Rwandan spring was very shallow, little more than damp mud. And so by growing it in pots above the water, Carlos replicated its natural habitat. Within a few short weeks, there were 50 specimens, all set to flower. So this is a crucial moment, because if this works, and it's clearly going to, you have in fact yourself saved a species.
If I didn't have this crazy idea, the whole species will be gone forever.
That's absolutely charming. Beautiful. In an environment with so many species and so many spectacular ones, it might seem odd to spend so much trouble in trying to save just one comparatively inconspicuous one. But the relationships within the rainforest are so complex and so extensive that the loss of just one can have a whole series of unpredictable consequences. The loss of a plant can mean the loss of an insect. The loss of an insect can mean that a bush loses its pollinator. The loss of a bush can mean that a mammal has lost its food plant. Nobody can say exactly when or if such things are going to happen. But to me, preventing it happening in the first place seems to make absolute sense. The story of plants spreads well beyond the wet zone. They have evolved to occupy almost every environment on the planet. They survive in regions of constant change. They thrive in soils that almost never see rain. And, as we will discover, they do much of their living in ways that go almost entirely undetected by us. I'm exploring the fascinating world of plants, from the most bizarre to the most beautiful. With new technology and in 3D, we can reveal aspects of their lives that are otherwise hidden from us. We can change time to discover a dynamic world of constant motion. We can change dimension to watch them interacting with insects. We can analyze how they communicate with color, with scent, even heat. And we can discover how fungi are not the enemies of plants, but their essential partners. And we can watch all these dramas unfolding in just one unique place, outside in the gardens and inside these spectacular pavilions of glass. The Royal Botanic Gardens at Kew. Our senses match what is important to us. Our eyes can detect just tiny little movements and see best during the day. Our ears can detect the frequencies of the human voice. But there are many things that are important to plants that we can't detect. This is an exploration of that hidden world. Plants may seem passive and inactive, but in fact they move. These are among the most mysterious. Sundews. The leaves, like those of other plants, use sunlight to help them grow. But their glistening tentacles get food in another way. They are traps. Plants, to grow properly, need sunlight and water and minerals and nutrients which they get from the soil. But in some parts of the world, in swamps and bogs, for example, there are very few minerals and nutrients in the soil. So plants have to get those things from somewhere else, and they get them from the bodies of dead animals. Each tentacle is tipped with a glistening droplet. It may look like nectar, and indeed many insects seem especially attracted to it. But it's not. It's a glue. It not only holds the insect fast, but clogs up the tiny holes on its flanks so that it can't breathe. Time-lapse cameras reveal that tentacles that have not been touched by the insect now start to bend towards it. How they detect the insect's presence, we still don't know. Finally, the sundew begins to fold its whole leaf around its prey. There will be no escape from this lethal embrace. Now the plant liquefies its victim's internal organs while it's still alive and absorbs the nutrients through its leaves. Other carnivorous plants don't require special photography to show how fast they can be. Darwin described this plant as one of the most wonderful in the world. It's a native of the coastal plains of North and South Carolina in America. The Venus flytrap. It catches insects with booby traps. At the top, the leaves are baited with a sweet nectar. But lower down, there are a few upright bristles. Triggers. Many things might accidentally touch one of them, so a single touch has no effect. But a fly crawling around on the leaf sipping the nectar is likely to touch more than one of the bristles. And if it touches two within 20 seconds, that's different. It's thought that the trigger hairs work by releasing a rudimentary electric impulse. The victim's desperate attempts to find a way out simply trigger more hairs and encourage the trap to close even more tightly. The plant begins to release juices rich in hydrochloric acid. It will take 10 days to completely digest its meal. But there's a carnivorous plant that moves at even greater speeds. It lives in the hidden underwater world of lakes and ponds. It's called Utricularia, bladderwort. These tiny wrigglers are mosquito larvae, and they are among its prey. The bladders that give the plant its name are not floats. They too are traps. Each bladder contains a partial vacuum and has a one-way entrance. By slowing down the action 240 times, we can see how they work. With the slightest touch, the door flies open inwards, sweeping the prey inside. It all happens in less than a millisecond. Utricularia is the plant world's swiftest killer. But most plants, of course, move very slowly indeed. Our cameras over a year can show just how dramatic such seasonal changes are. It's winter in Kew. It's so cold and the sun's rays are so feeble that plants can't grow. And leaves in winter can be a liability. A fully canopied tree could be uprooted by the winter gales, and in any case the flimsy leaves of oaks and beeches would be destroyed by the frosts. So many such trees stand naked and inactive throughout the winter. But eventually the sun begins to rise higher and higher in the sky, the days get warmer, and spring arrives. Light and heat-sensitive molecules inside plant cells are the triggers of germination and flowering. Timing is critical. Bloom too early and frost can kill a plant. Too late, and it can be swamped by the growth of its rivals. The first in flower are bulbs. The beds in front of Kew's farmhouse are transformed as they burst into colour. Then trees join the race. Cherries, and magnolias. Their flowers last just long enough to attract pollinators, and then they will fall. Meanwhile, in the woods, bluebells begin to appear. They must grow fast if they're to collect their share of the spring sunshine before the canopy develops overhead and cuts it off from them. But in some parts of the world, spring and summer may last only a few weeks. And the plants that live there have to complete their annual activities very swiftly. Kew makes special arrangements for them. This is the garden's newest glass house. It's the Alpine House. Inside grow plants from the mountains, where spring and summer are not only brief, but bitter. This house has been built to replicate alpine conditions, and it does it with this strange shape. Deep below ground, there's a labyrinth of concrete passages where the air is very cold. And as the temperature up here warms, so that cold air is drawn up through vents and flows over the plants at ground level. And then as it warms still further, it rises and escapes through vents at the top. And when the sun is really strong, it's got a further trick up its sleeve. It's usually the melting snow that stimulates an alpine plant to bloom, but here technology creates such congenial conditions that alpines flower without it. The alpine allium. Rosacea, a Himalayan plant which is closely related to ginger. And Sempervivum, a plant so hardy it can root in tiny cracks between the rocks. Mountain plants, it's true, are nearly all tiny, but they have the beauty and fascination of jewels. However, flowers did not evolve to please our eyes. Their function is to please insects. Nobody can be exactly sure how insects view the world, but it's certainly rather different from the way we do. We can see a part of the spectrum from red, which is long wavelength light, through orange and yellow and green and blue, to violet, which is short wavelength light. But insects can see even shorter wavelengths still. They can see ultraviolet. And we can use special cameras to reveal just what information that sensitivity to ultraviolet light reveals. We can move from how we see the world to how insects might see it. By looking at flowers in this way, we can begin to understand their true purpose. This flower, to our eyes, seems to have uniformly plain petals. But to the insect looking at it in ultraviolet, each petal has a white tip. So there's a circle of white, drawing attention to the bullseye, which is there where the insect can find pollen. This flower, which to our eyes appears to be plain blue, in ultraviolet light has white petals with lines running down it all the way round, pointing towards the centre. And this is the common foxglove, with, to our eyes, nothing more than a few random markings on its throat. But to an insect, there are more. These white lines probably act as landing lights which guide it to the nectar. The most important structures are often the most vividly coloured. The nectaries glow brightly, as does the pollen. The 4 o'clock flower blooms at dusk and has fluorescent pollen that attracts night-flying moths. This sensitivity to ultraviolet is just one way in which plants communicate with insects. Plants don't rely solely on colour to attract their insect pollinators. They also produce smells. In fact, as I stand here, I'm surrounded by a swirling vortex of perfumes of many kinds. But unhappily, the human nostrils can only detect about 5% of them. Insects do very much better. We can imagine microscopic droplets of these volatile oils suspended in the air. Many insects have antennae that are extraordinarily sensitive to them. Some can detect a concentration of just a few parts per billion. As a consequence, insects can smell a flower from as much as a mile away. But messages can also travel in the other direction. Some insects can communicate with plants. They do it with sound. Some flowers are extremely fussy about their pollinators. This is Gustavia from the Amazon rainforests. Here are its flower buds. Each one will only open for a few hours, and in that time it has to be visited by a particular kind of bee that buzzes with a particular musical note. Well, of course, there aren't bees like that flying around here in London, but we have ways of deceiving Gustavia with a tuning fork. All we have to do now is to wait for the flowers to open. Fork that resonates at exactly the pitch of Gustavia's bee will cause the stamens to vibrate. The motion releases pollen that would otherwise remain locked fast in the flower. The bee gains because it has exclusive access to a nutritious food source and therefore favours it. And the plant has a courier who is almost certain to deliver the pollen to the right address. We've highlighted Gustavia's pollen cloud because the grains are so fine they're impossible to see with the naked eye. But there is a way to examine even the tiniest pollen grain with an electron microscope. The colours are artificial. But these pollen grains are minute. This is cedar pollen magnified 7,000 times. Each grain contains a tiny bundle of the particular DNA that will fertilize a flower produced by another individual of the same species. But it has to get to such a flower. Some plants use animals as couriers. This mountain ebony pollen is sticky and clings to the fur of bats. Eelgrass pollen carries a bundle of filaments that will suspend the grain in water at just the depth at which the plant's flowers bloom. The wind-dispersed pollen grains produced by pines drift through the air with the help of tiny air sacs. Looking at the grains through a microscope reveals how astonishingly complex their shapes can be. Each is unique to one particular species of plant. Only grains of that shape and the right DNA will fertilize the flowers of the species that produced it. A pollen grain, when it arrives on such a flower, doesn't swim like the sperm of an animal. Instead, as this illustration shows, it produces a tube which goes down into the ovary at the very center of the flower. With each new season, new worlds reveal themselves. In late spring, the longer days and stronger sunlight cue the emergence of leaves. The gardens are transformed. Each plant arranges its leaves so that there is the minimum of overlap between them. They grow to fill all the available space, ensuring that every ray of light is harnessed by the green chlorophyll inside them. Up here in this walkway through the treetops, you can see the process as it happens. In just a few weeks, the trees clothe themselves in green. The amount they produce of leaves and shoots is extraordinary. In just 1 acre, it can weigh 4 tons. During the long, warm days of summer, leaves of all shapes and sizes grow in great abundance. And it's not just plants that depend on them. The rich foliage provides hidden habitats for whole communities of tiny insect herbivores and their predators. For many, leaves are food. Blackfly get what they need by stabbing their needle-like mouthparts into the veins of leaves and stems and extracting the sap. They don't even need to suck. The pressure inside the plant is enough to squirt the sap into their stomachs. Mealybugs are also sap drinkers. They produce a waxy powder from their skin, which most predators dislike, so that they're able to drink unmolested out in the open. Snails rip through the vegetation, rasping off mouthfuls with a long, file-like tongue. A single snail can consume a fifth of the weight of its body, shell and all, in a single day. So insects and other small creatures, some helpful, some harmful, flourish through the summer. This is the time when most of them reproduce, and they do so with staggering speed. Female aphids mate and lay eggs like other insects, but they also produce clones, babies that hatch from unfertilized eggs. And the clones themselves, even before they leave a female's body, are already pregnant with other clones. Such telescope generations enable aphids to infest a whole plant in a matter of hours. But aphids are themselves food for others, and assemblies like these don't go unnoticed by other insects. Among the most voracious are the many kinds of ladybird and their larvae. This is the young of a ladybird called Cryptolaemus, and it eats virtually nothing but mealybugs and aphids, when young and as an adult. This is the fast-moving young of a hoverfly. This larva of a lacewing is totally blind, but it doesn't need to see. It has an acute sense of smell and is especially sensitive to the pheromones produced by aphids. It attacks its prey by impaling them on a large hook in its mouth and then sucking them dry. And it has an unquenchable appetite. It will eat up to 600 aphids before it's adult. Most predators aren't fussy about the plants they live on, as long as there is prey to hunt. But one predator has formed a special partnership with a plant that looks rather like the insect-eating sundew. This plant, which is called Rorigula, also catches insects which get stuck to these sticky hairs on its leaves. But oddly enough, Rorigula can't digest insect bodies. Instead, it gets help from one particular kind of insect called a capsid bug, which lives nowhere else but on Rorigula. And the capsid bug runs around on these leaves without getting stuck, because its body is coated with a non-stick substance. And the capsid bug goes and feeds on the bodies of the insects that Rorigula has caught. And when an insect lands and is caught, the capsid bug runs across, sticks its mouth part into the insect's body and sucks it dry. Then it produces droppings which fall to the ground, and those can feed a rigula. The carefully controlled conditions inside Kew's glasshouses certainly suit plants, but equally they suit insects. So something has to be done to keep pests in check. One way is to introduce predators. Asian water dragons. They exist on a diet of mealworms and cockroaches. They quickly learn that the daily hosing down will drive the cockroaches out of the cracks where they hide during the day. There are also more subtle ways of controlling pests that visitors seldom notice. These cards have been coated with microscopic eggs of a wasp. When they hatch, the young wasps go off in search of their favorite prey, aphids. This one has discovered aphid pupae. It selects its target and injects it with an egg of its own. When the larva hatches within its host, it will eat it alive, just as others have done before it. These are the dried out husks of victims. Aphid mummies. Kew is starting its next great seasonal transformation. Autumn. Plants growing outside without the protection of the glasshouses must get ready for the bad conditions that are coming. Trees prepare to lose their leaves. The green chlorophyll inside them begins to break down to be reabsorbed. The bright colours are byproducts of the process. As the leaves fall, a new world reveals itself from beneath the soil. Fungi. Fungi can't photosynthesize because, unlike plants, they have no chlorophyll. In fact, they're more closely related to animals and are made of chitin, the material insects use for their skeletons. These are the fruiting bodies of a fungus. Their function is to produce dust-like spores which are then blown away through the woodland to grow elsewhere. But these are only a tiny part of the fungus. Most of the body of the fungus is beneath the ground, a tangle of tiny threads which extend for hundreds of yards through the forest. And we're now beginning to realize that those threads are essential for the growth and health of many of the woodland plants. The length of these threads is almost unbelievable. One specimen in America was found to extend across nearly 4 square miles. That's an area 16 times bigger than Kew Gardens itself. Technically speaking, it's the largest known living organism on the planet. Most fungi make a living by feeding on the dead tissues of other organisms, both plant and animal. They produce powerful chemicals that enable them to break down about 90% of all organic matter, including leaves and wood. In doing this, they release the nutrients into the soil that plants need to fuel their new growth in the spring. So fungi are essential links in the cycle of life. But some fungi establish partnerships with plants while the plants are still alive. And they are just as important. This is the Luckham oak. It germinated from an acorn in the year 1762, and it's one of the oldest plants in Kew. Its roots are covered with a fungus, but that's not an affliction. That's the reason why this tree was able to live for so long. Because the fungus can do something that the oak tree can't. It can extract nitrogen directly from the soil, and then the oak tree collects it from the fungus. And in return, the fungus takes sugars from the sap in the roots of the oak tree. So it's a mutually convenient arrangement, a symbiotic relationship. In fact, we now know that around 90% of the species of plants on the earth depend upon fungi one way or another. Kew cares for fungi just as it does for plants. A special underground world has been created for them. Here, thousands of different species are preserved in boxes. This is the fungarium. There are more specimens of fungi here than anywhere else in the world, 1.25 million of them. And scientists come from all over the world here to Kew in order to study them. The fungarium contains specimens that Kew has collected throughout the course of its 400-year history. They're stored for their potential value in science and medicine. Perhaps the most famous is this one. This is penicillium, a mold from which we get penicillin. There's another which is able to digest oil, and scientists are working to see whether it could be useful in cleaning up oil spills. But fungi can also be very sinister. This caterpillar has a fungus growing from its head. It's a species of cordyceps, a tropical fungus that has developed a gruesome power. They can infect the brain of an animal. One infects ants and causes an ant to climb up a grass stem, clamp its jaws on the top. And there, high up on the plant, the fungus kills it. A long, fruiting body then bursts out of the ant's brain. This elaborate behavior enables the fungus to rise high above the ground and shower its spores over great distances, and so reach new victims. The world of plants is still full of secrets, even though we have so many different ways of investigating their lives. One of the most famous species has been something of a mystery until only a few years ago. It may look like a tree, but in reality, this is just a single giant leaf. It's called the Titan arum, and it's a record breaker. But not because of what you see now. In a week or so, that green stem and the leaflets that grow on top will die and rot and disappear. But beneath the surface of the soil, there is a gigantic tuber, and it's from that the record breaker will emerge. This extraordinary event occurs just once every 7 years. It will take 2 months to complete. But this new growth is neither a trunk nor a leaf. It's the bud of the biggest flower in the world. As it grows, day after day, a huge spire, the spadix, rises from the center of the developing flower. And then one evening, as darkness falls over the forest, the giant flower opens. This surely is one of the most astonishing of blooms. I first saw one of these amazing flowers growing in the wild in the tropical rainforest of Sumatra. But why are they so big? Well, the function of the flower, like all flowers, is to attract a pollinator. And this plant gives off the smell of rotting flesh. But it does something else, something you can see with a heat-sensitive camera. This remarkable device reveals something astonishing. The white areas at the base of the spire are significantly hotter than the surrounding plant. It's heating up. At its hottest, the spire can reach 37 degrees centigrade, the same temperature as the body of a mammal. And as it warms, something else happens inside the flower at the base of the spire. hundreds of smaller structures begin to produce stringy pollen. The Titanarum is readying itself for the arrival of pollinating insects. Tiny sweat bees, and probably carrion beetles as well, are attracted by a combination of the powerful smell and the heat. Other flowers that smell of carrion also produce heat, so it seems that what is happening is that they are mimicking the warmth of the body of a recently dead animal. But the hot air produced in pulses from the Titanarum spire must have a different function. At night, a layer of cold air, still air, forms between the forest canopy and the forest floor. But the spire of the Titanarum, producing these pulses of warm air, pierces that barrier so that the smell of the Titanarum spreads out of the top of the canopy far and wide, so attracting insects, pollinating insects, from a long way away. If we could imagine such a spectacle, it would look something like smoke from a chimney, discharging heat into the night sky. It remains in bloom for just 2 days. And then it closes. Science has given us a glimpse into a hitherto unseen world. However, our journey of discovery has only just started. As technology advances, so will our understanding of the hidden world of plants. The final frontier of plant discovery is in the dry zone. In deserts, plants use an extraordinary range of adaptations in order to survive, by day and by night. And, as we will discover, new research into plants' astonishing time capsules of life, their seeds, could ensure that no plant need ever become extinct again. I'm exploring the fascinating world of plants, from the most bizarre to the most beautiful. With new techniques and in 3D, we can unravel their deepest secrets. We can move from our time scale to theirs. We can see how they struggle with one another, how they get help from some animals, but have to battle with others and survive against the odds. And we can watch all these dramas taking place in a way that is impossible in the wild in one unique institution. The Royal Botanic Gardens at Kew. In this living laboratory, we can discover plants' most extreme adaptations for survival. And we can glimpse Kew's tiny weapons in the battle to protect the future of all plants, seeds. Ever since plants first moved out of water and colonized the land, they've advanced into drier and drier places and evolved specialist adaptations in order that they can do so. Today, deserts cover about a third of the land surface of the Earth, and they're spreading rapidly. But some plants have developed some truly extraordinary strategies to enable them to survive in the driest of places. In deserts where water is scarce, one major strategy is to remain passive during the day when temperatures soar and only become active in the cool of the night. This desert, in Kew's Princess of Wales Conservatory, contains plants from arid regions all around the world. And in midsummer, one plant here does something truly astonishing. Don't be deceived by the shriveled, untidy appearance of this cactus. It is in fact one of the most remarkable members of the cactus family. It's called Hyla cereus, the queen of the night. It lives in Mexico, where during the summer at midday, the temperatures can reach a crippling 50 degrees centigrade. So during the day, it doesn't do much. But once a year, and for one night only, it becomes a thing of astounding beauty. The flowers usually open on a night of the full moon, and as they do so, they give off a smell which attracts night-flying animals, large and small. And as they get nearer, they can see the great white flowers bright in the light of the full moon, and they go to them to sip the nectar, and in doing so, pollinate the cactus. It might seem strange, even risky, for a plant to restrict its flowering to just one night of the year. But this strategy works for Hyla cereus. Its flowers are the biggest and brightest around, and they offer its pollinators a nectar bonanza. Bats. With the aid of technology, we can imagine them thousands of miles from their natural habitat here in Kew. Bats pollinate all kinds of cacti. In springtime in South American deserts, there is always a cactus of one kind or another in bloom. A multitude of species compete for the attentions of nocturnal pollinators using bright petals and powerful scent. The sweetest perfumes attract insects. But flowers that are pollinated by bats are rather more pungent. They give off the stench of rotten fruit. To nectar-feeding bats, that smell is irresistible. They fly from cactus to cactus, sipping up the nectar. Each bat can consume 1.5 times its body weight of nectar in a single night. Very tall columnar species produce flowers right at the very top of their stems, where they're easily smelt and seen and easily reached. Some provide additional facilities. Espastoa guanteri from Bolivia sprouts a landing strip beneath its flowers, a pad of fur on which the bats can alight without damaging their wings on the spines. But in Mexico, bats and cacti have an even more extraordinary relationship. Each year, bats migrate across 1,000 miles of desert from central Mexico to Arizona. Pregnant females, 100,000 of them, are on their way to special maternity caves in the north where they will give birth to their young. The bats get all the nectar they need to sustain their journey, and in return, they pollinate the cacti. This annual bat migration coincides exactly with the blooming of the night-flowering cacti, so the bats can fly along a nectar corridor. And so can cross a patch of desert that otherwise and at other times would be impassable to them. By the time the bats return with their pups, the cacti are able once again to provide the bats with food, this time their fruits. The bats carry with them in their stomachs the fruit and the seed it contains, and in due course they deposit those seeds with a nice little packet of fertilizer farther down the corridor. So the corridors are self-perpetuating. The bats, in effect, are cactus farmers. Perhaps the most extraordinary thing about these night-blooming cacti is that just a few hours after the flowers burst open, they begin to close. By the time the sun appears, they have already wilted and died. This is all part of their survival strategy. The closed petals form a protective shield around the newly pollinated seeds, locking vital moisture inside. The light of a new day reveals the bizarre nature of dry zone plants. These are surely some of the oddest looking species there are, and their strange shapes are a direct response to the harsh conditions. These plants must stay in the baking sun to collect the light they need, but they must also retain their moisture. Many do that by turning either their green stems or their waxy leaves into reservoirs. This extraordinary cactus from Mexico is covered in thick white hair. It's called the old man. This fur not only provides shade, but restricts the circulation of air around the surface of the stem, and that reduces water loss. In even hotter and drier climates, some plants avoid the sun altogether. This is Fenestraria, the window plant. It grows in the Kalahari Desert, with most of its body buried beneath the soil. Only the blunt, flattened tips of its leaves are exposed. Each contains tiny lenses which transmit the sunlight down through the vertical leaf onto its green photosynthesizing cells. Some desert plants that live in exceptionally hot, dry conditions take even more drastic measures. Leaves are very thin and have a large surface area, so they lose a lot of moisture in heat, and many desert plants have done without them altogether. Instead, the valuable green pigment develops in the stems, and desert stems are often very thick and swollen, and that enables a plant to store water in them. Not only that, but some desert plants have pleats in these stems, so that when there is a sudden rainstorm, those ridges can suck up all the moisture while it's there and expand in order to hold it. The stems of some of these species swell to such a degree that they become almost spherical. A sphere has the minimum surface area for any given volume, and that enables the plant to hold as much water as possible. This one is Copiapoa from northern Chile, where it never rains at all. But in fact, it doesn't need it. Under a microscope you can see why. There are thousands of tiny jagged structures on which the morning dew condenses so that the plant can collect it. But the ultimate is this plant. It's hidden between these light-coloured pebbles. Blossfeldia from Argentina. This is the only flowering plant that can withstand total desiccation for months on end, and then with a shower of rain or a little bit of water, it comes to life and produces a tiny little flower. This ability to wait for the right conditions is the trump card that enables many plants to survive in the dry zone. In many deserts, plants must endure months, sometimes years, of drought. They do it by slowing down their metabolism and going into a state of virtual dormancy. But when rains finally arrive, plants like these suddenly come to life. Their dried-out tissues absorb water like sponges. And once expanded, they use the moisture to grow. This primitive, rootless plant from the Chihuahua Desert in Mexico is a spike moss, Selaginella. It's also called the resurrection plant because of its ability to seemingly come back from the dead. Rain starts a complex biochemical change in its cells that enables it to ramp up its metabolism and grow very quickly while it can. But the most spectacular consequence of rain in the desert is an explosion of colour. Desert flowers are as colourful as any in the world. They have to attract pollinators quickly before the deserts dry out once again. But moisture in the soil can evaporate almost as quickly as it arrives, and after a brief bloom, they die. Desert plants can only grow when the conditions are right, and that may be only for a few short periods in the year. So many desert plants take a long time to reach full size. That agave there, for example, is over 40 years old. But during that time, it has manufactured food and gathered water and stored them in its great fat leaves. But it's not yet adult. This one is. This agave has started to withdraw that water and food from its leaves, so now they're beginning to crumple and wilt. And it uses that food to fuel the growth of this huge mast-like stem that grows from its center and will carry the flowers. And it reaches its full height at extraordinary speed. It can grow by 1/4 meter every day. It reaches such a height that here in Kew's glass house, panes have to be removed from the roof to let it through. This infrequency of flowering has given this species of agave a nickname, the century plant. So, why does the agave produce this huge, tall mast? Well, some plants are pollinated by insects, and you attract insects with smell. But this plant is pollinated by birds, hummingbirds. And birds have little or no sense of smell. To attract them, you have to exploit their very sharp sight. You have to produce flowers that are very bright and put them right at the top of a prominent, tall mast. Growing at such a rate demands considerable effort. For the agave, it's terminal. The act of producing that mast is the last act in this plant's life. Having done it and been pollinated, it dies. Thanks to their extraordinary survival strategies, desert plants are able to thrive in places where others would die. But that makes them the focus of much unwanted attention. There's a downside to success for a desert plant. The more water it stores, the more tempting it is for a thirsty animal to try and steal it. So desert plants have to have good defenses. The techniques they use can tell us something about the herbivores that try to feed on them. This Echinopsis from Argentina develops long, strong spines as a defense against large grazing animals, llamas. But such defenses also provide hiding places where an insect or a spider can keep out of harm's way. There are other ways in which a plant can protect itself. You can disguise yourself so that you become virtually invisible, as these stone plants have done. These are not pebbles, as you might think. They are living plants. These are lithops from the deserts of Africa, and their markings closely match their surroundings. What's more, they vary in colour according to the rocks on which they grow. That's grow in pale rocks, and those on reddish rocks. Or you can load the water you contain with a particularly strong chemical which animals might find distasteful. This is the peyote plant from Mexico, and its sap not only puts off animals, but has the property of suppressing pain. So the local people use it for that purpose, and also in their religious rituals, for it's also hallucinogenic. In colder regions, pine trees also have to conserve water, for during the winter, water in the soil is frozen and so beyond their reach. Little evaporates from their leaves because they've been reduced to stiff, tough needles. Like cacti, they also produce distasteful chemicals. The distinctive smell that you sense when you walk among pine trees comes from volatile oils that the trees produce in their leaves. It's a form of defense. Most insects can't bear it, but one can, the pine aphid. When that attacks, however, the pine trees have a second line of defense. They produce that volatile oil from the cuts made by the insects in even greater quantity, and that crucially changes the nature of the smells around the trees. Aphid infestation triggers a complex chain reaction from the pines. Each time an aphid bites, the pine releases oily vapor from the wound, which fills the surrounding air. This triggers the release of further volatiles from other branches, even other trees. The effect multiplies until eventually whole forests become cloaked in pine scent. This scent cloud attracts predatory ladybirds. They're as sensitive to it as sharks are to blood. This is the eyed ladybird, and it preys on pine aphids. It locates an infestation by following the trail of volatiles. And once there, it makes short work of the prey. It's a mutually beneficial arrangement. The ladybird gets an easy meal, and the pine tree gets rid of a pest. Some dry zone plants use oils to defend themselves from other dangers, not from insects, but other plants. This is a eucalyptus, famous for the oil in its leaves. It produces that oil in such quantity that under certain conditions it can form a blue haze above the tree. In fact, the Blue Mountains of New South Wales and Australia get their name from the haze that hangs over the eucalyptus forests sometimes. When the leaves fall to the ground and rot, the oil leaches out into the soil, and there, reinforced by more oil secreted by the roots, it acts as an inhibitor that prevents other seeds of other plants from growing around its base, so reducing competition for the eucalyptus. Another species use oils in a different way, and a more dramatic one. If the temperature raises to 32 degrees centigrade, those substances in the leaves of this cistus plant from the Mediterranean can spontaneously burst into flame. Reduce the cistus to a cinder, and the plant itself will never recover. But this is not a disastrous accident. The cistus has evolved to burn. Such extraordinary sacrifice ensures a different kind of survival of its offspring. The flames will also destroy all other plants from the surrounding area. And this gives the cistus a chance to extend its territory. From the ashes, a new generation of cistus quickly rises. Cistus seeds escape damage because they're enclosed in flame-resistant capsules. Furthermore, the smoke stimulates their germination. It has taken millions of years for such complex adaptations as this to evolve. But today, plants in the dry zone and beyond face a new threat. From rainforests to mountain ranges, the evidence is that plants across the world are disappearing in variety and number faster than at any other time in the Earth's history. Human beings are taking over more and more of the world's wild places. But human intervention can also be the key to their future survival. Kew is at the forefront of the effort. Its unique facilities enable scientists here to both measure the loss of species and work out how to prevent extinctions before it's too late. And a crucial resource in that battle is held in this building, the herbarium. Its collection of preserved and dried specimens contains samples of 90% of all known plant species on Earth. Here, almost unbelievably, there are records of every single specimen ever sent to Kew. It was founded in 1853. Now, staff process about 50,000 specimens that are sent every year from all over the world. It contains about 8 million specimens. It's the biggest repository of botanical data in the world and Kew's major weapon in the battle to save the plants of the planet. This vast data bank plays a vital part in monitoring the global health of plants. It's run by curator David Mabberley.
This herbarium, 8 million odd specimens, is actually a record of the vegetation of the Earth through time. There are some things which have gone completely extinct, and so all that's known of them is just some herbarium specimens. For example, this is a relation of the olive, which was known only from one island off the coast of California, and it hasn't been seen since 1873.
Really?
Even then there were only 3, and that's all that we've got left now.
Goodness. These specimens, though, are referred to, aren't they, for identification?
Yes, well, these are the standards, and the ones which are in these red folders like this are actually the ones upon which the original description of a plant was made, the so-called type specimen, and therefore this is the kind of gold standard. If anybody really wants to know what is meant by a particular plant name, they must refer to the type specimen.
The path to saving endangered species often begins here. For example, back in 1874, this specimen was sent back from the island of Rodriguez in the Indian Ocean, of a tree they called the café marron, a kind of coffee. It was preserved here, given a Latin name, and put in the herbarium. And then, about 50 years later, people on Rodriguez realized that café marron had disappeared. Then, in 1979, someone found a plant. Was it or was it not café marron? A specimen was sent here, compared with this specimen, and indeed it proved to be the case. So, from that single plant, a cutting was taken and sent here to Kew for propagation. From that single cutting, horticulturalists grew a handful of cloned specimens. But although they flowered frequently, they never produced viable seed. Without the ability to reproduce, the café marron was still doomed. So the plant earned the nickname the living dead. The daunting challenge of rescuing it was taken up by endangered plant specialist Carlos Magdalena. After several months of experimentation with heat and light, he finally managed to induce the plant to produce seeds. But when they germinated, the young plants had leaves so unlike the Café Marron he knew, he thought he must have made a mistake. That's quite different from Café Marron.
It's totally different, isn't it? Different color, different leaf shape.
So were you surprised?
Well, I was surprised in the way that I never seen them before.
This strange plant looked nothing like the herbarium sample. At first, nobody could be sure that it was even the same species. But as it grew, it changed. And eventually, it morphed into a recognizable adult plant. But what is the reason for this dramatic change as the Café Marron matures? The answer is camouflage. This is the most famous inhabitant of the island of Rodriguez, a giant tortoise. It loves bananas. Go on. But they also like green leaves, and that's their main food. So any plant growing close to the ground has very little chance of survival, while creatures like this are going around eating them. And that's the clue to the mystery of the Café Marron. When it's small, it produces leaves that are very thin and not even green. And the tortoise, whose eyesight is not very good, doesn't even see it. So he takes very little notice of leaves like this, and the Café Marron can grow. As it grows, it becomes a bit bigger, and still its leaves are thin and dark and rather inconspicuous. And it's not until it's really quite tall does the Café Marron plant produce its proper green leaves and its flowers. But by that time, it's well beyond the reach of a giant tortoise. So that is the solution to the Café Marron mystery. The plant produces two different leaves as a defense of being eaten. The Café Marron's survival is tribute to the skills developed here at Kew. But it is just one species. The ultimate aim is to safeguard all remaining plant species. And there may be a way of doing that by using these extraordinary structures: seeds. A 3D microscope magnifies them up to 200 times and reveals how extraordinarily complex the surface of a seed can be. No two species are the same. These images have been given artificial colours, but many of their shapes are beyond explanation. Some structures, however, have a clear function. They help the seed to achieve one of its main purposes, to travel. Many seeds rely on animal couriers. The American stick seed attaches itself to the fur or skin of passing animals with hooks and barbed spikes. The amazing sticking structures of such hitchhikers inspired the invention of Velcro. Some seeds carry a little packet of nutritious fat, which persuades an ant to take it back to its underground nest, where the seed, having surrendered its fatty reward to the ants, can germinate in safety. The seeds of orchids are minuscule and produced in their millions. They blow away like dust. In contrast, this much bigger seed has a large flat membrane which serves as a wing, so that it can float great distances on the wind. Other wind-dispersed seeds, like the yellow paintbrush, have a honeycomb texture. Such complex sculpturing enables seeds to catch the slightest wind current and ride thermals, travelling long distances from their mother plants. But these images also reveal the incredible toughness of the seed's outer capsule. This strength may be the key to the survival of all plants. For seeds can survive all kinds of hardship. This plant is called the pincushion and grows in South Africa. And this individual specimen is something of a miracle. In 1803, a British man-of-war captured a Dutch merchantman coming back from the Cape of Good Hope. And on board, in the cargo, they found a packet of seeds. When they got back to Britain, the seeds went to the Tower of London for quite a long time. But eventually, they found their way here to Kew. And one of them germinated and produced this plant. After 200 years, just shows how long seeds can survive even without help. This ability to endure has inspired Kew's latest groundbreaking project. Its ultimate goal is to ensure the survival of every remaining species of plant on Earth. The work takes place deep underground in a labyrinth of sealed vaults that are encased in steel and concrete. It's called the Kew Millennium Seed Bank. Its contents are so valuable that it was specifically designed to withstand the impact of a bomb or an air crash. Inside these vaults there are seeds gathered from plants all over the world. In fact, as much as 10% of the world's known species are represented in there. The Seed Bank project is this gigantic freezer full of seeds in sealed jars. The conditions inside are perfect for long-term storage. But the job is aided by the very nature of seeds. The seed is the stage in which a plant can remain dormant, waiting until conditions for germination are right. Inside each seed, there's a store of food. Outside, there's a tough protective shell to guard against predation or damage. In fact, a seed is a kind of time capsule that can live for sometimes a decade, sometimes even centuries. The aim of the seed bank is to prolong that period as long as possible. To do that, they clean the seeds, dry them, put them in jars like this, and then keep them here at minus 20 degrees centigrade. How long they will survive under these conditions, nobody knows, but it's certainly going to be for a very long time. New samples arrived at the seed bank every day. They are first identified and studied in microscopic detail by Chief Morphologist Dr. Wolfgang Stubbe.
The latest report from Israel claims that date palm seeds have been found in King Herod the Great palace in Masada, and they germinated after 2,000 years. So that is possible, and this is the principle the Millennium Seed Bank is built upon, that seeds can survive for millennia if necessary.
The longevity of most kinds of seeds is unknown, so they must be regularly checked. Samples of seeds are periodically removed from the bolts and germinated. If most grow, the whole batch can be left in the bolts for another decade. But sometimes a sample fails. Like these anemone seeds, which, although germinating in sterilized conditions, become choked with fungus. When this happens, the scientists must find out why and how to prevent it happening again. The seed bank project is still in its infancy, but the evidence is that there's no time to lose. There are already seeds stored here from plants that are now extinct in the wild.
The problem is, what many people don't understand, is that if a species goes extinct, it means it is gone for us forever. There was 5 mass extinctions in the Earth's history. After every mass extinction, it took between 4 and 20 million years for biodiversity to bounce back to pre-extinction levels. Now, clearly we cannot wait 4 million years for life to bounce back. So if we don't keep seeds here and this plant species goes extinct, it will be lost to mankind forever.
Thankfully, there's a great momentum behind the seed bank project. Over the next few decades, these shelves will be filled to capacity. There's enough space here to hold seed from every single species of plants on this planet. But this place is not just an insurance policy against the ultimate apocalypse. This is of huge value right now. For wherever we discover that a plant is teetering on the brink of extinction, we can now bolster its numbers with seeds from here and so ensure that no plant species on Earth need go extinct. There are an estimated 400,000 different species of plant on the planet. We can't possibly understand the lives of each and every one of them. But here at the Royal Botanic Gardens in Kew, one of the birthplaces of scientific botany, we've begun to glimpse their extraordinary world. still in the forefront of botanical research, helping to ensure that we not only understand plants, but protect them in all their astonishing variety. And here we can see how plants in all habitats and environments are intricately connected with animals and with fungi. Not only do plants give the world much of its beauty, they are indeed the very basis of all life on Earth.